Kuzuzangpo, welcome to Bhutan e-learning. I am Diki and this lesson is on chemistry, key stage 5, class 11 to 12. For today's lesson, you are going to study about spdf orbitals and spdf block elements. By the end of this lesson, you should be able to identify sp, d and f orbitals, and also you should be able to classify the elements into spdf block elements. Okay, so first thing, how are electrons distributed in an atom? In order to understand this one, think of a family owning a house. The family as a whole will be owning one house, and if you look further into it, each family member will be occupying one room in the house, one room each in the house. Just like that, electrons in an atom occupy orbit, specific orbit, and further these orbits are divided into orbitals. The electrons will then occupy specific orbitals in the atom. So here you can clearly see in the diagram here. So this is the orbit, and this one, the subdivision of the orbit is our orbitals. Okay, now what is orbit and orbitals? Orbit is a well-defined path. So if you look into this one, the electrons revolve around the nucleus in a well-defined path that is known as orbit. And what is orbital? Orbital is the region around the nucleus where the probability of finding the electron is highest. So if you look into this diagram, this space around the nucleus here, the space that is the orbital. Okay. We already know that electronic configuration can be written following Aufbau's principle. So this is what the electronic configuration of an atom looks like using Aufbau's principle. So what does this number 1 stand for in this electronic configuration? It stands for main energy shell or orbit. It is also called as principal quantum number, and it is represented by letter N. What does this S stands for? It stands for orbital or subshell. So it can be linked with angular quantum number, which is also represented by letter L, and it basically gives the shape of the orbital. And what does this number 2 stands for? It stands for number of electrons. Here you have to know that the number of electrons will differ for different orbitals. Okay, now let's look deeper into principal and angular quantum number and subshell. So there is a relationship between principal and angular quantum number and the subshell. Here in the table you can see principal quantum number, angular quantum number and subshell. If the principal quantum number is 1, what is the value of angular quantum number? So angular quantum number can be determined using this formula here. L, the value of angular quantum number will be equal to 0 to n minus 1. So when principal quantum number is 1, the angular quantum number will be equal to 0 to 1 minus 1, giving you a value of 0. So what is the value of subshell here? How many subshells are there when the principal quantum number is 1 and when the angular quantum number is 0? It shows that there will be only one subshell, and that one subshell is S. Let's have a look into this principal quantum number here, which is number 2 here. So here using this formula, we can clearly see that angular quantum number has 2 values, L is equal to 0 and L is equal to 1. So which means it has 2 subshells. And what are those 2 subshells? They are S and P. So P subshell starts only from principal quantum number 2. If you look into principal quantum number 3 here, there is 3 values of angular quantum number 0, 1 and 2, which means there will be 3 subshells or 3 orbitals S, P and D. Okay, so principal quantum number 4, it has 4 values of angular quantum number and 4 subshells S, P, D and F. Okay, now let's look into the shape of atomic orbitals. As you can clearly see, there are different shapes of atomic orbitals here. So, why different shapes of atomic orbitals? This is because of the cluster of electrons found around the nucleus. This cluster of electrons found around the nucleus, here this is your nucleus and these are the electrons found around the nucleus. This develops into different shapes depending on the energy level. Okay, so now we are going to look into particular shapes of different orbitals here. Firstly, s orbital. So, s orbital has spherical shape, which means the probability of finding 90% electrons surrounds the nucleus, forming a spherical shape. Okay, so this is example of s orbital here. So, one s orbital. So, this is the shape. So, this is how the electrons rotate around the nucleus. Okay, so what you can see here is 3 different energy level, 1s, 2s and 3s. And here you can clearly see that the subshell or orbital is all s, which means there will be spherical shape here. If we look closely into it, though they belong to S subshell, they differ in their shapes. Why is it so? This is because if we apply certain amount of energy to the electrons will jump to next higher energy level, and there the probability, if we look into 2s, the probability of finding electrons will be more around this area. And again to this 2s electrons, if you supply extra energy, the probability of finding electrons will be more in 3s subshell. Let's look into p orbital. So, p orbital has dumbbell shape. There will be 3 different orientations of p orbital depending on the position of the orbital along the axis. So, this is what p orbital looks like here. So, the probability of finding electrons will be in this direction as well as in this direction. So, let us look into examples here. So, this is one example of p orbital 2px. Here the lobes are aligned along x axis. So, that is why it is known as 2px orbital. So, let us look into 2py orbital here. So, in 2py orbital, the lobes will be aligned in y axis. So, it is known as 2py orbital. Okay, so 2pz orbital. In 2pz orbital, you can see that the lobes again aligned on z axis. So, it is known as 2pz orbital. Okay, so if we look into these slides here, we can see there is 4p, 3p and 2p. Though they belong to same subshell or orbital, they exhibit a little different shapes. Why is it so? Again, the answer is same. When extra energy is applied, the electrons tend to move to higher energy level. So, thereby forming a little different shape from one another. Overall, this is what the p orbital shapes are for 2px, 2py and 2pz. D orbital. So, d orbital has double dumbbell shape. So, d orbital can have 5 orientation depending on the position of the electrons along the different planes. So, 3 dyz orbitals, it looks like a clove leaf here. So, the 2 lobes are aligned along yz plane cutting through yz axis. So, this is the last example for d orbital. So, 3d z square orbital. So, here the electrons are aligned along z axis, it looks similar to 2pz, and also along the center forming a shape of a donut. So, overall these are the shapes of d orbital having 5 different orientation, but you do not have to know all these 5 different orientation. For your label you just have to know that the d orbitals have double dumbbell shape. So, f orbital usually do not have a definite shape, it is quite complex. Most of the time f orbitals have diffuse shape, thereby it does not give you a definite shape. So, if we look into an example here, it looks somewhat like this, but you have to know that f orbital do not have a definite shape. Okay, so now I have a question for you. If the value of n is 3, what is the value of L? Based on the value of the L that you have obtained from here, determine the number and shapes of the orbitals. So, this is all about the shapes of the spdf orbitals. Now, what I want you to do is you can draw the outline of modern periodic table and then mark the block as SP, D and F block. After you are done with that, you can identify 2 elements from each block. Okay, so when you are done, you can check your answer with this one. So, here in this diagram given to you, you can clearly see that modern periodic table is divided into 4 blocks. You have S block, P block, D block and F block. Okay, now you can think about this question here. Did you ever wonder why these elements are placed in particular block? Why is element A placed in S block? Why is element B placed in P block? So, you can start pondering on this question. In order to answer the question that I posed earlier, you can write down the electronic configuration of nitrogen, sodium, zinc and cerium using SPDF notation. After this, you can locate the elements and periodic table to identify their respective blocks. Okay, so you can check your answer with mine here. So, these are the electronic configuration of the elements provided to you. Firstly, sodium. Let us look into sodium. Sodium, this is the electronic configuration. And if we look into the outermost shell configuration, it is 3s1. For nitrogen, it is 2p3. For zinc, it is 3d10, and for cerium, it is 4f1. Now, if we try to locate these elements in their respective blocks, we can see sodium located in S block, nitrogen located in P block, zinc located in D block and cerium located in F block. So, what you have to know here is the placement of elements in their respective block is determined by the last shell. To which block does this last shell enter, to which subshell does this last shell enters, that determines the block of that particular element. To simplify, if I say if the element's last electron has entered S subshell, it means it will enter S block. If the element's last subshell has entered P subshell, it will be entering P block. Let us look into electronic configuration of outermost shell. So, these are the elements, these are the blocks, and this is the general electronic configuration of outermost shell, or we can call it as balanced shell configuration. So, you can have a look for few seconds here. Okay, now why know this? Why do you have to know the electronic configuration of the outermost shell? This makes it very easy for you to figure out the block of the element or predict the block of the element. If you know the balanced shell configuration of the particular block, you can easily predict the block of the particular element. Okay, so in order to understand it more clearly, I will be showing you few examples here. So, example, magnesium. So, here you can see that it is the balanced shell configuration is 3s square, which corresponds to ns square. That is the general configuration for S block element, and here for magnesium it is 3s square, which means its last orbit is 3 and the last orbital is s. The last electron is entering into s orbital, so it will be belonging to S block. From here, when you look into last orbit, it is number 3, which means it belongs to period number 3. Let us have a look into neon. The last electronic configuration is 2p6, and this is the general configuration for p block element. Here when we look into this one, we can figure out that last orbit is 2 and last subshell is p, which means it belongs to p block and it belongs to period number 2. Chromium here. So, for chromium, the last subshell is 3d5. Though there is 4s1, for d block element, the last subshell will be 3d5, which corresponds to n minus 1 d1 to 10 and s1 to 2. So, this shell here we can call it as the penultimate shell. So, for d block, what you have to know here is the last electron will be entering the penultimate shell rather than the last subshell. So, by looking into this one, we can clearly say that this chromium belongs to d block and it belongs to period number 3. Let us look into cerium here. So, the last electron, similar to d block, the last electron it enters F, 4f instead of 6s. So, this is the general electronic configuration. So, that is why because the last electron enters F, cerium is known, it comes under F block. So, there is again a question for you. The outermost electronic configuration of the elements are provided to you. So, by looking at the outermost electronic configuration, what I want you to do is, I want you to predict the block of each element here. Okay, so, let us check on the answer. For 1, it is 3p3, which means it belongs to p block. 2, 3d5, meaning it belongs to d block. Question number 3, it is 4f1, meaning it belongs to f block. Let us look into the transition element and its configuration. You already know that the group 3 to 12 are transition elements. So, transition element basically are the d block elements. Here usually transition elements will have their last electron shells, incompletely filled. or partially filled. Most of the d block elements can be considered as transition element except for 3: cadmium, zinc and mercury. Why is it so? This is because the penultimate shell, the shell where the last electron enter, is completely filled for all these 3 elements. So, they cannot be considered as transition elements, but they are d block elements. Example here, this is the configuration of cadmium. You can clearly see that penultimate shell here, it is completely filled, 3d10. If you look into cobalt, it is 3d7, which means it is partially filled. Let us have a look into expected valence shell electronic configuration and observed valence shell electronic configuration. The expected, when we follow the F-Bausch principle, we will usually write the electronic configuration of copper like this, where D will have 9 electrons. But the observed valence shell electronic configuration is something else. It is 3d10 here. So, why is there such irregularities? This is because the energy difference between the penultimate shell and the last subshell is very small. So, a last electron will be entering the penultimate shell instead of the last shell. Then this is the most important reason here, the half filled orbitals are and completely filled orbitals are more stable compared to partially filled orbitals. So, you already know electronic configuration can be used to predict period number and block. With this again, you can use this formula to calculate or predict the group number of S block, P block and D block element. Okay, so we are coming to the end of lesson. Take home message for today's lesson is: number 1, the elements are placed in their respective block based on the subshell that the last electron enters. Number 2, the shape of the orbitals. P has spherical, S has spherical, P has dumbbell, D has double dumbbell. Number 3, the balanced electronic configuration can be used to predict the group, period as well as block. And number 4, the half filled and completely filled orbitals are more stable than partially filled orbitals. So, this is the assessment here, which will be assigned to you through Google Classroom, and your class teacher will be assisting on it. So, thank you for today's lesson, and I will see you in your next lesson.